All right, this is how to calculate the shear from a hodograph from one height to another height using both either visual techniques or numerical techniques. I'm assuming when you're watching this that you already know how to read a hodograph. That's pretty important. If you don't, then I'd advise learning that before you watch the video because you might be a little bit clueless. And aside from that, let's get in. First off, when you're calculating the shear from one point to another, I'll say this right here is the surface and this is 6 kilometers. You only include those 2 points. The rest of the hodograph is irrelevant. The shear vector is just this. I say shear vector because shear has direction and a magnitude. It's a vector. If you want to calculate the shear from 0 to 6 kilometers, the shear is literally just shear equals W 6 kilometers minus W 0. That's the 0 to 6 kilometer. Shear is the wind at 6 kilometers minus the wind at 0 kilometers. Now, if you look at this, you see we have 55 knots at 6 kilometers and 40 knots at the surface. If you just do, let's say the speed shear, let's say you want the speed shear, would just be 55 knots minus 40 knots equals 15 knots. So you could say this is 15 knots of shear. And if you say speed shear, then yes, the speed has changed by 15 knots. However, the displacement, the change in speed, is more than 15 knots. And that's because of the directional component. As I said, it's a vector. The change in direction, it's changed by almost 180 degrees. So, if you want to calculate the actual magnitude of change, you would need to convert this to Cartesian or just count the circles. If you're doing this visually, it's pretty easy. This is each circle is 10 knots on here, so it's 10, 20, 30, 40, 50, 60, 70. That's around 80 knots of shear. Now that I'm eyeballing it a little bit. When you're doing it visually, you have to eyeball. I'm basically just finding the distance between these two, and I'm just eyeballing. Right here, it's gone 1 ring of distance. Here, it's 2 rings of distance. When you're going like tangent to the rings, it's a little bit more difficult, but just to eyeball it. If you're doing visually, you only need to eyeball it. However, let's say you're doing it computationally. Let's say you need the exact shear given these starting conditions. The first thing you're going to want to do is convert the wind to Cartesian coordinates. Now, you see up here, I have the wind is blowing from 60 degrees, and the wind is blowing from 260 degrees. Converting it to Cartesian, I find it a lot easier to just say, in this case, it's 10 degrees from the axis, so it's 10 degrees above relative to the x-axis. And in this case, it's around 170 degrees. Oops. Sorry, that's just blatantly incorrect. I apologize. We measure relative to the y-axis in most mathematical systems. So it's around 80 degrees from the y-axis. The 6 kilometer wind is around 180 plus, I don't remember what I had, I think it was 60. So that's 240. 240. In this case, this is the way the wind is blowing to, not the way the wind is blowing from. That's just because that's what the hodograph is. The hodograph shows what it's blowing to, not the way it's blowing from. If you're new-ish to meteorology, that's kind of intuitive, but that's usually not how it's taught. Now, if we want to calculate the Cartesian component of each vector, which we will need to do, first we need to know what the Cartesian vector is. The Cartesian coordinates, or Cartesian vector, it's just a position vector. A position vector is just the coordinates where something is. If we wanted to find the 6 kilometer wind, the wind at 6 kilometers, we could say 55 knots and 80 degrees from the y-axis. Sure. Or you could do x and y components similar to how you learned how to graph in like 3rd grade. I don't know when you learned to graph. So we could say the wind would be equals, it's trigonometry. If you haven't taken trig yet, I'm shocked you're doing meteorology. I think you learned trig before. I don't know when you learned that. But the wind would be the magnitude times a vector. Oopsies. magnitude times the vector sine 240 degrees cosine 240 degrees. If the x-coordinate is sine of the degree, the y-coordinate is the cosine of the degree. I always confuse those two. I probably should not. Anyway, though, if we do that, we'll get the wind equals negative 34.6 and then exactly negative 20 knots. What does that mean, you might ask? That means we split it into a component vector. The wind is going to the west at 34 knots and to the south at 20 knots. Why does that matter? Well, let's say we do the exact same thing for the 6-kilometer one. We have the speed is 55, we have 54 knots and 10 knots. Rounding to the ones place. And if we plug it back into the equation of shear equals that one minus that one, we have shear overall, the shear vector, equals 5410 minus 34.6 minus 20 equals, I'm rounding again, that's around 8930 knots. And wow, okay, I did. 80, and if we want to do that, if you want to find the magnitude of shear, you just do the Pythagorean theorem. So shear would just equal square root of 89 squared plus 30 squared. That gives us 93.9 knots. So that's why you can have the actual change in speed of only around 15 knots, but you can still have 94 knots of shear. Now, if you see a big map of shear values, that's using this value. If you see a hodograph analysis program like SharpPy, that's using this value. I don't know really any place where you actually see the individual speed and directional shear components used. There's probably some place that my brain isn't thinking of right now. Otherwise, it wouldn't be taught. But yeah, if you see 93 knots of shear, that's why. So yeah, that's how to calculate shear.